In this module, we will discuss the reliability evaluation of the composite power system. In the composite power system, we evaluate the reliability of the combined generation and the bulk power system. As we have said before, that in the multi-area reliability, the constraints of transmission within an area are reflected only indirectly while calculating the capacities of the tie lines between the areas. Now, if there is a need to consider the internal transmission limitations in greater detail, then we come to the composite power system reliability evaluation. So one of the objectives over here is that if you want to optimize the relative investments in generation and transmission, or you want to study the trends in resource sharing, or sometimes you want to consider the effects of the generation in the transmission system reliability analysis. And also now we have more dispersed generation like wind power, solar power, storage, and cogeneration. So if you want to study the effect of all these sources on the reliability of the power system, then composite power system reliability evaluation is useful. Now, in trying to compare the multi-area and the composite system reliability, they are similar in many ways. The major difference is in the detailed modeling of the transmission system. In the composite system reliability evaluation, the transmission network is modeled in more detail than in the multi-area reliability evaluation. So as a result of the more detailed representation of transmission, there are more nodes than in the multi-area reliability evaluation. Also, there is an issue of the network flow model. In the multi-area, you can use either the linear transportation type of network model or DC flow method. But in the composite power system reliability evaluation, the network model is either DC or AC. And the methods could be either deterministic or they could be probabilistic. In the deterministic methods, just like in the generation reliability, the main idea is to maintain adequate service under most likely changes, but when the changes go beyond that, then be prepared to accept some degradation of performance. A famous one is the N-1 criterion. You can postulate, that the power system will not suffer in reliability, supposing one transmission and one generator fail, or one transmission and two generators fail, and so on. So this kind of analysis would be the deterministic analysis. In the probabilistic models, we can have the analytical methods, we can have the Monte Carlo simulation, and we can have hybrid methods, which are combinations of these two methods. Let us first discuss the models of the components that are a part of the transmission and the generation network. These are generating units, transmission lines, transformers, buses, circuit breakers, and weather is an important component because the transmission lines, they are exposed to the weather, and also the common mode failures of the transmission lines especially, they are important. The generating unit models, they can be 2-state or 3-state. For a 3-state model, you have the up state with full capacity, derated state with partial capacity, and down state with zero capacity. A 2-state model will be, of course, a special case of the 3-state model because this state is not there. But you can also have more states of the generating units. The modeling techniques are capable of handling generating units of larger number of states. Generally, the problem is with the data to support higher number of states. The transmission lines, the failure rates and the repair rates are assumed to depend upon the weather. So the Markov model for this would be, this is the normal weather and this is the adverse weather. This is the mean duration of the adverse weather, this is the mean duration of the normal weather. So for the component, you can have the failure and the repair in the normal weather, you can have failure and repair in the adverse weather. And these rates, as you can see by these primes over here, they will be different than the ones in the normal weather. So the weather can go from the normal to the adverse with this rate, and from adverse to the normal with this rate. It should be noted that when the transmission lines are in parallel, then you cannot just use an average failure rate. See, mind you, here you can calculate an average failure rate. If the lines are in series, then you can use an average failure rate. But if the lines are in parallel, then if you use the average failure rate, your reliability evaluation will be too optimistic. You need to consider the two states separately because most of the overlapping failures, they happen in the adverse weather, and if you take the average, you tend to dilute that possibility, and therefore your calculations may be too optimistic. The transformers and buses, they are basically treated as two-state devices, either up or down, and then there are failure rates and the repair rates, associated with these models. But for the transmission, for the transformers and the buses, we typically do not consider the failure rates different in the adverse weather and the normal weather, but just choose an average failure rate. How about the failure modes of the circuit breakers? See, the circuit breakers can have either what we call a ground fault, and in this sense, this behaves just like any other component, like a transmission or a transformer. But there are two other failure modes which can have a very serious effect on the reliability of the composite system. One is the failure to open. See, circuit breakers, because of the problems within the circuit breakers or because of the problems in the protection systems which control the circuit breakers, you can have the probabilities that if the circuit breaker is supposed to open because of the fault on the line, the circuit breaker may not open. So if the circuit breaker does not open, then the backup protection will come into play and the backup breakers will open. But when the backup breakers open, then you will have larger area which will be isolated than if the breakers open properly. So for that reason, the failures of the breakers not to open can lead to larger outages and also can lead to the cascading outages. The other possibility is what we call the undesired tripping. See, here the breaker may open when it's not commanded to open, and this can also create problems with the reliability of the bus power system. Common mode failures is also important because it can happen that if there are two transmission lines on the same tower and something happens over there, like the tower crashes or because something like a helicopter comes and hits the transmission lines, then both the transmission lines may be knocked down. So this is one of the models used for the common mode failures, where from here you can go directly to the two-stage tower. Now, although the common mode failure rate may be smaller than the normal failure rates of the transmission lines, but the effect can be more serious. Now, this is only one of the models for the common mode failures, but there are many models which have been proposed for the common mode failures. Now we come to the network solution methods. One of the simplest network solution methods is what we call the linear network flow model, or also the transportation flow model. Here basically what you do is you try to see that the Carlo's first law is observed, which means that the flows into a node and out of the node they are equal. But the impedance or the admittance of the transmission lines are not taken into account. Of course, you have also to observe that the constraints of generation are satisfied, which means that the generation is less than the maximum possible, and the flows in the lines have to be within limits in both directions. The next level of the flow model is the DC load flow model. Here, these are the bus angles, and this is the matrix of the susceptances, and M, these are the injections into the nodes. So here we assume that the voltage of each bus is 1 per unit, but the angles, they change. So the flow in any line is given by the difference in the angles multiplied by the susceptance of the line between node I and J. Then of course you have to follow the constraints for generation and for the transmission capacities. Now, in this model, you do consider the admittance, but you assume that the voltage at every bus is 1 per unit. Now, the AC power flow model handles both active and reactive power flow. In the DC model, we are concerned only with the power flow, which is active power flow, or what we call the real power flow. But in the AC, we are concerned with both the reactive and the real power flow. Now, what are the different methods for analysis? One method, of course, is the straightforward enumeration. You can enumerate all possible states and perform flow calculation to see that whether that state satisfies the load or not, or if there is any problem with that state, and then knowing the probabilities of all the states, you can find the reliability indices. However, as we have seen in the multi-area reliability, this approach is not feasible for the bigger power systems. So, what we can do is that we can have some techniques where we do not have to consider every possible state. So we need to have some process of contingency ranking and selection. So this process typically considers the two steps. One is the ranking of launch and generator outages or overload conditions and voltage problems using a performance index, and then the selection of the contingencies from this ranked list. Other possibilities are state-space truncation. You can say that in this approach, the contingencies of only a certain order are considered. For example, you can say that you will consider the contingencies only up to the second order, which means that we will not worry about the failures of more than 2 lines or more than 3 lines and so on. The other is what we call the implicit enumeration. So if a state is identified as a failure state, then we assume that all the states resulting from this state by degradation of the components are also failure states. So for example, the methods based on the minimal cut sets, they use this basic idea and thereby reduce the burden of having to examine every possible state. Then there is a method called the state space pruning. So here we take away the states which can be easily identified as the success states, and in this way we enhance the probability of failure of the residual state space. So then if we perform the Monte Carlo simulation on the residual state space, then the convergence will be much faster, and once you get the index from the residual state space, you can transform it back to the original state space. Then the other idea is what we call the non-overlapping failure regions. So here the idea is that the higher order outages are restricted to circuits in the same electrical neighborhood. So therefore you can pick up what we call the focus area and do the analysis on the focus area. So if there's a problem and you are going to have a loss of load, then there are certain remedial actions which can be taken. And these remedial actions will be different if you are using the DC power flow or the AC power flow. And this gives a list of the various remedial actions which can be performed to possibly alleviate the loss of load. You may not be always successful. Now coming back to the methods, if we take the contingency ranking and selection, then we need to realize that the goal of the contingency selection techniques, what's the ultimate goal? The ultimate goal is that we have a large set of states which are the set of all possible contingencies. So we want to determine the subset that will cause system failure. So the contingency ranking and selection, the whole goal is that how do we efficiently identify this subset which cause system failure. Perhaps there is no contingency ranking and selection method which can do this job perfectly. The only method which can do the job perfectly is the exhaustive enumeration. But that's not feasible for systems of any real size systems. So other possibility would be to rank contingency by the first solving each contingency using a DC power flow, but this would be very time consuming. This is like exhaustive enumeration. So a faster but less accurate method is ranking the contingencies based on the severity, which is based on some kind of a performance index. So the performance index is first defined to provide a measure of system stress, for example, overload, over voltage, and so on. Then a technique is used for predicting a delta PI, the change in PI when the component is outaged. Then these delta PIs are used to rank the contingencies in terms of their severity, that which contingency is more severe, which is less severe, and which is less severe, and so on. Then you go to that list and you start from the top and you analyze these contingencies in more detail and see that which contingencies actually are causing loss of load. And then once you hit the contingency or a set of contingencies in the consecutive order so that there is no loss of load or there is no problem, then you stop. Now you have to realize that this is not a foolproof method, because when you stop at a certain level, it is still possible that there may be the contingencies below that which can cause loss of load. So there is a certain amount of approximation in all these contingency ranking and selection methods. The other method is, which is most widely used in the composite system reliability evaluation, is the Monte Carlo simulation. Monte Carlo simulation is of two kinds. One is what we call the Monte Carlo sampling, or the non-sequential Monte Carlo simulation, and the other method is the sequential Monte Carlo simulation. Now, in the sampling method, you can describe it like the following. Let us say X is a system state, and the system state consists of the component states. So these are the components, and this is the system. So Xi is the state of the ith component, and X is the set of all possible states. So all these X's are members of the X, and probability of the state X is given by Px. Then we can define fx as a test function applied to verify whether the state X is able to satisfy the load or not. So the expected value of fx, this test function, will be fx multiplied by its probability and sum it over all the states, right? So this is how you calculate the x is a random variable, and f of x is a function of this random variable. So this is how you find the expected value of a function. Now if you are trying to compute the loss of load probability, then the EF will be defined as, the F will be, for the function f of x will be defined as follows. The function x is 1 if there is a load curtailment in state x, and 0 otherwise. So basically when you apply this over here, you are adding up the probabilities of all the states which are loss of load or where there is a curtailment of load. So in random sampling, what you do is that instead of considering all the states, remember that in this function you are trying to find out the probability of all the states which cause loss of load. So in random sampling, you try to find the estimate of that function instead of computing it completely. So what you do is that you have state x, which is element of x. They are sampled, and then the expected value of f is computed as you pick up for each sample f of xi, add them over all the samples and divide by the number of samples. So this gives you the estimation of the E of x. This is actually the estimation. And the variance of the test result can be given by this, the variance of the function divided by the sample size. So this is the variance of the estimator, of the estimate of the E of x. So this is the variance of the estimator. Now we do not know the variance of f. So therefore, instead of using the variance of f, we estimate this one by this equation and then use the value over here. So basically, you can compute the variance of the estimator, and you also know the average value or the estimated value of the estimator, and then you can find out the coefficient of variation that we will show later. And as you perform the sampling, you try to see, okay, when is the coefficient of variation lower than a certain specified value, and then you can start your sampling. This is how you proceed. You start with 0 sample, then you pick up the first sample, and so you have to select this state by sampling from the probability distribution of P of x. Then you calculate the function fxxi, which means it is either 1 or 0. Then estimate your mean value and the variance, and calculate the uncertainty of the estimate, which is the variance. If the uncertainty is acceptable, then stop, otherwise go to true. And as I have said before, the uncertainty is judged by the coefficient of variation. So how do you select the system state? Because you do not have the probability distribution of all the states of a system. So basically, you pick up each component because you know the probability distribution of each component, and then you combine the component states to form the system states. So the system state is sampled by sampling states of the equipment or the components, and the principle of proportionate allocation is used, which means that the states which have higher probability should be sampled more number of times than the states which have lower probability. So in practice, you have the probability distribution or the cumulative distribution of the random variable, which is the states. You pick up, you generate a random variable between 0 and 1, and then you put that value on this axis, and then you see, okay, for example, if the random variable is here, then the state is here. If the random variable is here, then the state vector is here, and so on. So the coefficient of variation can be found from the standard deviation of the estimate and divided by the expected value. So if you substitute all these values from the previous discussion, then the equation becomes the variance square root, that is the standard deviation, and this is the sample size, and this is the expected value. So if you rewrite these equations, you will see that what happens is that if the probability that you are trying to estimate is small, then you will need a larger sample size, and if the probability is big, then you need a smaller sample size. So therefore, the systems which are highly reliable, they take a lot longer to converge in Monte Carlo simulation than the systems which are low reliability. So, as you can see that the convergence depends upon the variance. If the variance is high, the convergence takes longer time. If the variance is low, then it takes shorter time. Now there are techniques which are called the variance reduction techniques, and they sometimes have been used to improve the efficiency of the convergence. And two of the methods which have been frequently used is, one is the control variable method, and the second is the method based on the antithetic variables method. Now how about the sequential simulation? The random sampling is generally a preferred method whenever we can use it. And random sampling is much easier to use when the components are independent, because you can sample the components independently to construct the system state. When, however, there are dependencies, then it becomes more difficult to use the random sampling, and therefore we try to use the sequential Monte Carlo simulation. In the sequential, what you do is that you are in one state of the system, for example. So you try to generate the sequence of states as it progresses in time. So if you are in one state, then the system components, they are in particular states. For example, component 1 may be up, component 2 may be up, component 3 may be down, and so on in a given state. So what you have to do is to find out that when will that state make a transition to another state, and to do that, what you have to do is you have to find out how much time will each component take to make a transition. And obviously the component which takes the minimum time will be the one which will make the transition first. So first we have to have a method to find out that how to find the time of transition to the next state. And the method used is similar to the one used in the sampling that we have shown. That here is a random variable. For example, this could be the uptime or the time to failure. So let us say this is a probability distribution of the time to failure or the uptime. You draw a random number, put it over here, and treat the value here. This gives you a time to failure of the component. And similarly, you can find the time to repair or time to anything that you want to find out if you know the probability distribution. So basically what you do is that if you are in a state, then you find that time of transition or time of change for all the components, and then you say, okay, what's the minimum time? If this time corresponds to, say, component P, and Tp is the time to change, then basically your system will change the state at Tp after this time. So the simulation time can be advanced. This is the time at the nth transition, and this is the time which will take to the next transition. So the time can be updated. And then the time, remaining time on the other components which have not made the transition can also be calculated. So this is called the residual time to transition of the component time. So you keep on doing that and keep on generating the states, and then of course you can use your statistical methods to estimate the probabilities, frequencies, whatever you want to estimate. So that's it.